In this episode, we are going to simulate splashes. First of all, we need to extract the peaks of the mesh as the source, copy the tsunami, and import it into a new geometry. Then we extract the source based on the cusp attribute, create a group. When the cusp attribute is greater than the set value, allow the points to enter into the group. Usually the tsunami collision happens in a low position. If the emission position is too high, it's abnormal, so we can limit the height. When both conditions are met, let the points enter into the group. But do not set a very low position, otherwise the tsunami will look plain with only a few splashes. For now, we set a rough height based on the buildings. Later, we'll handle its flat top caused by limiting height, and it will become lower then. So keep the height for now. Add a blast to extract the group del. Here we can convert from points to primitives. Primitives produce a larger area of source than points. Okay, we tweak cusp to control the source area. So how to determine a proper value? We mainly see the deleted areas on the mesh. If they're too small, then the distribution of the particles will be too uniform and lack details. If they're too large, it means the particles will be insufficient. So it's fine with some spaces like this. Well, let's handle the flat top issue. If the top of the source is flat, then the top of the pop simulation will also be flat, which is abnormal. So we will make it undulating. Here we can add a bound. But we need to apply these two transform nodes to the bound. Duplicate it. Toggle the template flag of this bound. This one is for moving the tsunami downward slightly. Here we can tweak their order and connect the bound to transform 2. Then we export the bound. Drop down a null node. Copy it. Uncheck the convex polygons, then the split edge is removed. Check the breaker polygons. The subdivision is too high by default. After all, the scene is too large. Disconnect divide 1. Increase the size. We just subdivide the lower primitive. We can see that the primitive number is 4. Reconnect them. Create a mountain. My thought is to make an undulating surface through mountain first. Then we perform a calculation between this mountain surface and the cusp group. Tweak the offset values. Set display flag on the blessed one. Adjust a proper height and element size of the mountain. Let's move it up a bit. Later, we will subtract the tsunami above the mountain through group calculation, pin the current 3D view, and then lift up the lower primitive of the bound a bit. Create a group. Now we got an undulating top of the tsunami source. Here is too low, which is not what we want. Tweak the offset. Then we make a calculation between group 1 and group promote 1. Group promote 1 belongs to a primitive group, So we need to convert group 1 to a primitive group. We need a group transfer. Add a group combine. Only keeping primitive groups is fine. Input the name of the new group here. Select subtraction. And then set display flag to blessed one. The top becomes undulated now. Let's check if there's something wrong. There are some small loose parts. There are areas where the tsunami is not contained by that bound, like the edge here. Because with the mountain node, the bound cannot completely match the tsunami mesh. We expand the bound a bit more. Looks good now. Let's check the source of the tsunami we attained just now. Check its height. Perfect. It's almost the same height as this building. No need to be higher. Next, we will apply the current source to emit particles, but it is too large, so here we simulate it with several frames, otherwise the computer cannot make it. Well, let's first find the farthest place in the camera view. Switch to top viewport. The water splashes should be simulated at the first frame of our render range, so we start with a negative frame around -30. We can apply 2 frames for now. Solo the buildings. Then we add a box. Adjust its range. Roughly to this place. Contain the buildings on both sides in this box. Jump forward to take a look. Whiten it a bit. Make it higher. Okay, keep the range for now. Then we get the source in the box. This group name is the same as the previous one. Let's change it. Next, let's set up velocity for the source. Here, I'd like to set it according to the normal directions, since they're determined by the directions of waves. Display normals. This way, the velocity can match the dynamics of the waves, which is more reasonable and with a better effect. Add position to normal. Assign the result to P. This way, we can view the velocity intuitively through displacement. The current effect is not obvious at a multiply constant. Obviously, the default normal directions cannot work well, so we need to adjust the normal directions in different axes separately. Let's first separate them. Then strengthen the needed axes. We first reduce the strength of the y-axis. There appear some peaks now. But we do not make them too sharp. A little bit is good. Then we set the strength of the z-axis. Here we can set a relatively larger value. This way the directions of velocity can be more varying. Then the x-axis. We can see the source is displaced in both the positive and negative directions, which is caused by the different directions of the normals. To make them consistent, we can add an absolute. But there is another problem. The current direction is positive on the x-axis, but our tsunami is moving in a negative direction, so we give the multiplier a negative value. We can see the surface with displacement is a bit too smooth. To get more details, we can add a turbulent noise and multiply it with the adjusted normals. This way the velocities will be more random. Delete it. Here we control the intensity of the normals with the amplitude of noise. Select sparse convolution noise. With it, the displacement is more random as it has both positive and negative values. Also, add an absolute to unify the directions. Promote the parameters. Increase the amplitude a bit. It is too broken now. Let's lower down the frequency to get some large-sized displacement variations. Setting the velocity in this way, the particle dynamics will be more random. If the displacement effect is too broken, the whole dynamics will be too uniform. We increase the roughness to get some small details. Assign the adjusted normal directions to the velocity. Click the velocity here. Now the directions of the velocity are consistent with the normal directions. Here we add in the displacement to the position is to make it easier to see the effect. Disconnect it for now and check the size of the velocity. It can be seen that some velocity lines are a bit shorter, but some are much longer. We can adjust the attenuation here to reduce the length varieties of the velocity lines. Look here. When the attenuation is 0, the velocity lines are of the same length. When the attenuation gets larger, their lengths vary a lot. So let's reduce it. It's good now. Display the displacement. Offset it a bit. You can test it to find a desired effect. Here I just apply my tested values. Till now, the source is basically done. The displacement is just for viewing velocity. So we need to restore it back to the mesh without the displacement. We subtract v from p. Okay. Well, the velocity lines are still kept. We can see they still lack some randomness. So drop down a point velocity to add some more details. Select Keep Incoming. Then check Add Coral Noise. It's more random now. No need to check Animated because the velocity lines are animated by VOP here. We simply set a proper swirl size to avoid it being too noisy. Let's see the scene. This is a human of nearly 2 meters. Basically, setting the swirl size to 5 meters is proper for this scene. Alright, the velocity setting is finished. Next, we build up to simulate pop. My thought is to simulate the pop first and the flip later. Before that, we need to set the start frame of the simulation range. Actually, pop simulation is easy to get a good shape. Around 30 frames are enough. So I set it to -30. In the pop, just use first context geometry and scatter on the surfaces by default. But constant birth rate needs to be larger. The life expectancy needn't to be so long, since we still need to simulate flip later. For life variance, a little bit is fine. Tweak the seed a bit. Increase inherent velocity. The tsunami moves forward very fast. If the inherent velocity is not greater than the velocity of the tsunami, then pop will be swallowed up by the tsunami. So it's necessary to set a larger value. Then we drop down a pop force to disturb the particles during simulation. For the amplitude, we can refer to that of the velocity of the tsunami source. Here, set a similar value here, so that pop force 1 can affect the particle dynamics properly. If it's too small, then the pop force 1 can hardly work. Besides, we can also refer to the scale of the human model. Basically, about 2 meters is good for revealing the details. If it's smaller than this, the ocean will be disturbed too much. Next, let's animate offset. It will be better with some changes. Then we add a gravity force, add a ground plane, we reduce the bounce. Then the particles won't bounce obviously when hitting the ground. Otherwise, it will look abnormal. Next, we need to set the buildings as collision objects. When the tsunami flows in, it can collide with these buildings. So let's set these buildings as collision object. Come into the scene. We only allow the buildings on the right side to collide with water. There are high polys and low polys. Here we just need high polys. The low polys are mainly as reflected objects when rendering. We can separate them according to their different groups. This can be set according to your own project. Now all the low polys are removed. Here we only keep the buildings on the right side. We add a box. Switch to top viewport. Display the tsunami mesh. Box up that building too. Lift up the box a little bit. These buildings are totally in the box now. Select bounding object to group them. Add a blast. Check delete non-selected so we can get the collision buildings. Convert them to VDB. Set a low res to prevent the computer from crashing. As long as we can see the rough shapes of the buildings, it's fine. Well, it is a bit too low now. Raise it a bit. The rough shapes are reflected and without any obvious errors. Perfect. We cache for 1 frame. rename it. So this is the collision object on the right. Next, we import it into the DOP network. Add a static object node. Put the collision objects into proxy volume. Select volume sample. Then solve it to take a look. Display the collision objects. Everything looks good now. Play to see it. Well, most of the particles are in the back of the tsunami instead of going forward. Increase the inherent velocity to let more particles go forward. Besides, we can delete the particles in the back of the tsunami since they will be blocked by the tsunami. We extrude the tsunami mesh to get a volume, then group and remove the particles inside. Just extrude the area within the camera view. We have gotten the area when subdividing the tsunami within the camera view. Here we can directly apply that group. Add a blast and check delete non-selected. OK. Note that the tsunami source is overlapped with the tsunami mesh. To avoid deleting the source, we can separate them by adding a time shift. Offset the time by 1 frame. It's OK now. Import the volume into DOP network. Add a subsolver. Paste its path. Then the particles inside of the volume are all selected. Remove them. Before caching it, remove the unused attributes. Only keep velocity, which can save some disk space. Set the output path. Connect the start frame of the cache range with the DOP simulation. Let's cache it. Drag it to take a look. Oops, there's no cache. Let's check it. It's good here. Oh, the particles are cleaned by the clean one, with the 2 checkboxes being checked. One is remove unused points. The other is remove degenerate primitives. The DOP particles meet these 2 conditions, so they are cleaned. Let's see the preview in DOP for now. There are not enough particles. We will add more later. Another problem, the particles go too far. If we simply flip with the particles, the flip will definitely splash too far. Let's take a closer look at here. Roughly starting with this frame, these particles are emitted. Let's check the source. Here is displaced quite a lot, so we need to limit its velocity. Add a fit range node after this terminus node. The velocity of the particles are controlled by the amplitude of the noise. We can link the source max of the effect to the amplitude of the noise. Add a ramp to control the velocity in more detail. The right side corresponds to the max velocity. We raise the mean velocity on the left to keep it roughly the same as before. Add a point in the middle. Increase the value here to keep the velocity of this part the same as before. As for the max velocity area, no need to limit it too much. Increase it a bit. Let's compare it with the previous effect. Duplicate the attrib VOB node and delete the two newly added nodes. You see the large velocities are limited now. Let's check the simulation dynamics in the camera view. The particles move forward in this direction. I want them moved toward the camera a bit, which can be more shocking. Here we need to adjust the directions of the source. This is z-axis. We add a value to it. The particles move toward the camera now. Let's check the changes in the camera view. Do not shift the direction too much. Maintain generally the same direction as before. Otherwise, the dynamics will be abnormal. The particles are not enough. Let's increase them. Add a pop replicate node. Shorten its life expectancy. Set a slightly longer life expectancy than the source to keep more particles. Set a lower value for life variance. Set a smaller constant birth rate. It's unnecessary to get too many particles, in that too many particles in the pop source will lead to too many particles in the flip, and it will take a very long time to cache it for testing. We can test in simulation to get a proper number of the particles. Select cone for shape. It's more like a water drop. Uniform scale determines the distance between the replicated particles and the original particles. Set a relatively smaller value. A large value can lead to rather scattered particles. Check add noise to randomize the dynamics. Set a smaller frequency to avoid it being too fragmented. To view the effect intuitively, we create a grid. Drag it here. Add the same noise for it. Select simplex noise. Then connect it to color. We simply adjust the frequency here. It's good now. Then tweak the amplitude. There's no special requirement of it. Set a proper value as needed. Let's come to pop replicate. We set the same value for frequency and amplitude as the grid. Decrease the inherent velocity a bit. I prefer flying splashes instead of clumps. Select Add to Inherited Velocity. Adjust Variance. Here, I'd like to demonstrate for you how variance works. Drop down a pop location. This is the same variance we just mentioned. Set a velocity for y-axis and add a gravity. Set 0 for variance for now. Let's see how it goes. Basically a straight upward line. When we set a larger value, the particles are spread in radial direction. This value determines the radius of the emission. When we set a lower value, the radius will be small. Here, I just need a small radius. A too large value can lead to a widespread. Okay. Uncheck the two checkboxes. Cache it. Now it's done. Let's take a look. We can see some obvious problems after increasing the particles. The particles splash too high, display the tsunami and buildings. Some particles are higher than the buildings. They are too high and far. This is just the pop simulation after all. When we simulate flip based on it later, the splashes will be higher. Similarly, with such far simulation, the flip simulation will be farther, just like this sketch. So we need to fix it. We can lower down the inherent velocity. For example, set the value to 3. A small partial cache is enough for testing the dynamics. It's more efficient. Alright, let's cache it. It's done. Let's take a look at the simulation of the first 50 frames. Compared with the previous version, its range is smaller. So the previous problems are basically fixed. But there comes another problem. Look here. Display the tsunami mesh. The tsunami here is not totally covered by the particles, which is not a problem in the previous version. But with that small inherent velocity, the particles cannot cover the mesh well. So this way doesn't work. We return to the previous inherent velocity and try setting a larger gravity to avoid the particles splashing too high. It's not a normal way, but based on our needs. When it comes to a proper pop simulation, on the one hand, it should cover the tsunami mesh and the source well. On the other hand, we need to consider how far the flip simulation we want. These two aspects determine how far the pop simulation should be. Alright, let's exclude the collision ground before caching. Here it is. We don't need it. Exclude the ground through ID. We can see the object ID is 0. Alright, let's cache it.